In an earlier video, I said that I was going to watch the lunar eclipse on September 27th, 2015, and attempt to find the distance to the moon using a simplified method. You can see the original video here, or if you're on mobile, click on the card. But I finished processing my data, and here are the results. I tried to get some video through my telescope, but with poor results. Fortunately, I had my camera up and running. On the lower left is the raw footage of the eclipse, sped up of course, but you can see all of the times I had to adjust the camera because of the Earth's rotation. In the middle is the footage with the sudden jerky bits taken out and the moon partially aligned, and on the lower right is the final stabilized footage where the moon is just centered in the shot the entire time. Next, I took the footage and rotated it so that I could show the Earth's shadow as stationary and the moon passing through it. It should be noted that for artistic reasons, the south is roughly at the top of the screen. I also chose to include the Earth's actual size rather than just assuming that the umbra was the same size as the Earth. It's a relatively minor step that I didn't do in the original video, but it makes a great improvement. The Earth's actual diameter is about 1.29 times larger than the umbra at the approximate distance to the moon. So after making the circle that traced the umbra, I simply scaled that up by 1.29 to get the Earth's imprint. The penumbra was also found the same way, but it wasn't very important for the calculations. Taking the starting and stopping points of the video footage and measuring the distance covered in relation to the Earth's diameter, I can see that the actual distance the moon traveled is about 4/5 that of the Earth's diameter. Since the diameter of the Earth is known, it's easy to get a distance. Next, I divide this distance by the total time, which turns out to be 9,600 seconds. This gives me a tangential speed of 1.8 kilometers per second. Then, multiplying this by the 27.3 days, converted to seconds of course, gives us the circumference of the lunar orbit, assuming a circular one. Dividing this by 2 pi gives the final distance to the moon of 405,000 kilometers. Comparing the speed and the distance I got, you can see that I found both the fastest possible speed and the largest distance. This actually makes a lot of sense if you know about orbits. Remember that the eclipse on the 27th, 2015 was actually a supermoon eclipse. That means that the moon was as close as it ever gets to the Earth. The thing is, when an object is orbiting, the closer it gets, the faster it moves. Just like a falling object speeds up as it gets closer to the ground. So when the moon is at its closest, it's also at its fastest. Since I approximated the circumference of the lunar orbit based on its velocity, I ended up with a larger number. However, due to the weirdness of orbits, the speed actually dictates how far the maximum distance from the Earth the moon gets during its normal orbit. Just like how a ball thrown up into the air, where'd my ball go? Just like how a ball thrown up into the air has all the speed it's going to get as soon as it leaves your hand, this speed is what actually decides how high it makes it into the air. And in the same way, the maximum speed that the moon goes as it's close to the Earth dictates how high, how far away it will get at its most distant point. In short, I'm very pleased with the values that I got. Both the maximum speed and the maximum distance agree with the accepted values to within the number of significant digits I had available. But you don't have to take my word for it because you can science it.